and get started.
Just like this big.
So, any questions about the announcements? I like to do the announcements because it kind of sets the stage for what I'd like to accomplish in a lecture period. But I couldn't decide what we would accomplish, so we have a lot of question marks. So right off the bat, are we going to get through Chapter 3 today? I'd personally like to know. I think we will, but I don't know. If we do get through Chapter 3, then Friday your homework will be due. So if we don't get through Chapter 3, then we'll finish up Chapter 3 on Friday, and then your homework will be due Monday. So sorry to leave you on that roller coaster. So it looks like this is one of those cases where actually we're going to get through Unit 1 material before we have the Unit 1 exam. So the Unit 1 exam, I said the earliest would be Wednesday, and it's going to stay the earliest is Wednesday, even though we're done lecturing over that material. Which means that actually we're going to have to go ahead and start into Unit 2 material, which there's 3 chapters in Unit 2 also. If you remember, the syllabus says it's chapters 4, 5, and 16 for Unit 2. So we'll just see. But either way, it looks like I said we're going to start new material. I'll give you the handout slides on either Friday or Monday for Chapter 4. Okay? So, Friday, though, you want to be here because I'll go ahead and have a review sheet, what I call a review sheet, for your Unit 1 exam on Friday to give to you. So my review sheets basically break it up like Chapter 1, Chapter 2, Chapter 3, and it says kind of key terms that you might run into, concepts or whatever, on your unit exam. Okay? So I basically make up my unit review sheet after I make up my exam. Okay? You all cool with that? Remember, the exam has 3 parts. It's going to be multiple choice, vocabulary, and short answer. Yeah.
Do you? I know in the other class you recorded the
review. Yep.
Can you do that?
Yep. I'll go ahead.
On YouTube?
Yep. Yep. A good question up here. The review session I'll record and then I'll put on YouTube and then I'll put it under Twitter. The link under Twitter. Yep. Because the review session not everybody can come to, so. Every once in a while, I'll have the review session in class just because that's the way the timing works. But usually it's outside of class, right after class, when we're all hungry for lunch. So, any other questions? All right. So let's keep talking about temperature. So we're kind of switching gears. We talked a lot about different things that influence temperature. Is this the right slide? I guess it is. I need to go back one. Yeah, that's where I need to start, right?
No.
One more?
Effect of geographic position.
Really? So we didn't do any of this? Whoa.
We're 4A. 4A.
Right here?
Yes.
Thank you. Okay. Yeah, I don't think we'll get through Chapter 3 today. We'll see. Okay. So I didn't bring my big globe, but I'll grab the small little world over here. Okay. So we're going to continue kind of picking 2 locations and looking at a climatogram with those 2 locations. First off, one of the things that Benjamin Franklin realized, so Benjamin Franklin grew up over here, like our northeast, right? I'm not really good with that stuff, but one of the things he realized was the direction that wind patterns come from. So if you're over here, what directions do you look? Do you look this way, this way, this way, or this way for what our weather's going to be next in general? Yeah, I agree. Generally, we look toward our west. And the snow systems, not always, because we can have something come up from the south or something come down from the north. Okay, but generally, yeah. And we'll be talking about that later. Actually, we have a prevailing wind down here in the troposphere called the mid-latitude westerlies. It's basically a wind that kind of just blows in this band, okay, of latitude. So this is all to say that if you are, the 2 locations, I'll go ahead and put this other part up here. The 2 locations we're going to see here in a minute are basically on either side of the United States. It's a little bit what we say confounded, because we said that what kind of temperature do we have over here in the Pacific? It's cold. It's cold, yeah. And this is generally warm, yeah. But what this says is if you have a wind, a prevailing wind, like the mid-latitude westerlies, this location over here that is actually on the windward side, okay, is going to have more of an effect of the Pacific Ocean than these folks over here at the Atlantic Ocean. Because we said oceans tend to they kind of dampen your swings, okay? So this guy over here is going to have less of an effect of his ocean because the wind is generally blowing from this direction. That's all it is, okay? So like I said, the two locations are one over here in the Pacific Northwest, over here at the Northeast, okay? So remember how these climatograms work? Basically, we're looking at January through December. So kind of the swing. Okay, which one has more swing? The New York one has more of a swing. And again, he just has a less of a, the Atlantic should kind of be a good kind of a what we call a moderating effect, kind of, so it doesn't have much swing, but it's downwind. This other one has to do with mountains too. Okay. And in this one, the two locations we're going to look at are kind of near each other. But again, well, have you ever heard of like how dry this is on the other side of what I generally call the Rocky Mountains? It's dry over here when you get on the other side of the mountains. And we'll be talking more about that too. But basically, on the other side of the mountains, they don't have the effect of the oceans like the wind side of the mountains. I don't know. It seems kind of a strange point to me. So the two locations separated by a mountain are Seattle and Spokane. To me, I'm not really sure you could call Spokane really a maritime or a coastal location, but I think that's kind of what your author's point here is. The fact, like we said, the wind blows from the west to the east, okay? Seattle definitely gets the lion's share of the moderating effect of the Pacific Ocean. So again, if we compare the two, Spokane being on what we call the leeward side of the mountains, okay, it's not only is it dry, but it doesn't have the Pacific Ocean to kind of moderate, so it has a greater temperature range. So if we find Spokane's in blue. So.
Can you go back one slide? I'm sorry.
I can go back one slide.
Okay, thank you.
Mm-hmm. So those are two kind of mountain things, but like I said, I think it's a stretch to call those two maritime or coastal locations. All right, what else we got? Here's one for you. We talked about cloud cover, and this is kind of almost, I call it a deja vu slide because we really did kind of talk about this, that if you have clouds between you and the sun, they're going to reflect the light from the sun, will reflect the radiation from the sun. Clouds during the daytime when the sun is out will have a cooling effect. And at nighttime we said clouds will have a warming effect. So here we go. How do you find, So this actually now is not a climatogram. We're switching gears. This actually is the course of one day. So along the x-axis down here we have midnight to midnight, okay? And we said that if your day is clear, okay, that would be the red line. Okay, if you have no clouds, okay, what's going to happen is during the daytime, your temperatures are going to be warmer, and at nighttime, your temperatures are going to be colder. So that's no clouds. So we've been talking about ranges. I say with no clouds, you've got quite the range going on, okay? If you have clouds in place during the daytime, you got clouds, it's going to be cooler, and at nighttime, it's not going to get so cool. So it's going to be warmer at nighttime, cooler during the daytime, so it has less of a temperature range. I buy that. So this is another look. Now we're switching back to climatograms. So this is just for one location, though. One of the cool things, there's a lot of cool things about this course, but you probably heard of tsunamis, or not tsunamis, sorry. That doesn't have to do with weather per se. You probably heard of monsoons. Okay, so locations that have monsoons or experience monsoons have a dry season and a wet season. Okay, And so actually what you're seeing is kind of a location with a monsoon. And to show its dry season and wet season, these bars right here are precipitation. So throughout the year, and you read the precipitation over here. So for instance, how much precipitation does it get in September?
Lots.
A lot. That's right. September, we're talking, you know, looks like what, 60 centimeters, 23 inches of rain in that 1 month. There's quite a bit. And we'll talk about why that is. But, so we said with precipitation comes clouds, and with clouds comes the effect that we were talking about. So actually this location is in the northern hemisphere, so you figure in, you know, June, July, it's going to be the hottest it should be. But remember, it's got clouds. So the point here is, you know, you don't see it ramp up and get hot in June and July. Why? Because it's raining every day. Okay. So that's kind of the gist of all of that. Chronic cloud cover. Yeah, it doesn't sound like a place I want to be. I get down if it's a little bit cloudy. Okay. Okay. So another thing that we talked about is we talked about the term albedo and reflectivity. I'll put this whole slide up here. Okay. Albedo is basically kind of the fraction of light that is that an object bounces back. Percent reflectivity is related to albedo by a factor of 100. So percent reflectivity is like out of 100 parts. So one of the things that you guys already know is that which is going to be more reflective, the snow and ice or the ocean? Snow and ice. This exactly is more reflective, has a higher albedo, exactly. So this is like we talked about, like if you go skiing. This is my pair of sunglasses. Okay, if you go skiing. And the sun is shining, you can actually get a crazy sunburn from skiing. You know, that's why they have their goggles and they got sunburn around them. Maybe it's just in the movies, I don't know. So one of the things that's happening, and we'll talk about this with global warming, is it's called a positive feedback effect. Not positive because it's a good thing, but positive just because it feeds on itself. Positive because it keeps getting bigger and bigger. So here's the deal. As we get warmer temperatures, okay, what's going to happen is that this is going to melt, okay, and as that melts, basically you're going to have a lower albedo, more absorptivity. So that's it's what we call positive feedback, okay. So the point is as the amount of our ice sheet in both hemispheres is getting less, then that means the snow and such is less, and we have more absorptivity, you know, less reflectivity, okay? So it's warmer. All right, now this is where I thought we were going to start today. So switching gears, kind of pulling everything together, looking at the entire world, not just North America or kind of this here and that there. Things to keep in mind that we already talked about. We said with regard to latitude, remember latitude is how close you are to the equator. You guys would tell me that it's cold up here at the poles and it's warm near the equator, which is awesome, which is true. Now, the thing, I'm pointing to the equator here. This is the hot spot. Okay, we'll talk more about this hot spot. But this hot spot in June and July migrates north. Okay, summertime in the northern hemisphere. This hot spot in December and January, or December, November, January, migrates south. The hot spot does. And that kind of migration we're actually going to see on the next slide. The other thing is we said, and you're going to see this on the global, when we look at the globe here, a map of the Earth, okay, we said that if you are on a coast, okay, we said that the ocean is going to help kind of it's going to kind of keep your temperatures the same, kind of, if you're on a coast. We're going to see that in a minute. The other thing goes right here, and we said, you guys told me that the Pacific is a heck of a lot colder and the Atlantic is a lot warmer, the ocean. And actually that works for all continents. Bless you.
Thank you.
So the other day we switched here from North America to South America, and we found the similar pattern. We said over here on the west, as it turns out, actually they it's going counterclockwise around their ocean gyre, and they end up with it's cold over here, just like it's cold over here, and it's warm over here on the eastern side, just like it's warm over here on the eastern side. Actually, that has consequences. It all has consequences, but when we get to talking about hurricanes, one of the things you guys would probably tell me is that for hurricanes to do their thing, they need to be nice and toasty, warm water. Okay, so actually that's a player in the formation of hurricanes. Okay.
Is that why they watch the temperature of the...
Yes, that is, the temperature is one of many factors to see if you're going to have a hurricane season or not hurricane season, strong one or a weak one. Yep. Okay. Now, that's where I thought we started. So here we have January. So remember I said December, January. I'm hoping you're kind of thinking along the lines of, even though we're winter, they are summer down here. So the hot spot should be kind of south of the equator, and it is. Okay. These are isotherms. Remember what isotherms are? They're connecting locations with the same temperature. So it might be hard for you to read, but I can kind of zoom in. So this isotherm right here says 80 Fahrenheit. And what they did is they did it in English and metric. So 27 degrees Celsius is the same thing as 80 degrees Fahrenheit. So not so surprising, if you move either direction, it gets cooler. So this isotherm is 70. Okay, this isotherm is 60. All right. But if you're like me, something that's striking, I mean, check that out. You're like, really? Look how, remember we said if your lines are close, we call that a tight gradient or a steep gradient. If your lines are close, it means you don't have to go very far to go ahead and get in this case, a 10-degree change. So here it must be changing quickly, and also it must be very cold. Purple is the coldest here, color anyway. So we have purple up here, and we have no purple here. Well, actually, this is not a good example because this is not an equinox. This is actually, these guys are having summer here. Sorry, my bad. We're having winter. That makes sense. All right. So that is in January, and this is in July. So I'm going to draw a line. I think I'll choose blue. Let me draw a line through the hot spot here, and I'm going to draw a line through the hot spot here. Does it look like it moved? This one looks like it's almost on the equator, but this one actually really moved up. And, yeah, we do have some purple down here. They're having winter down here. We're having summer here. Okay, now this is another look. These look like isotherms. In fact, when I was getting ready for this lecture, I'm like, wait a minute, those aren't isotherms. Okay, they actually are our ranges. These are our temperature ranges. So in other words, if you are here, one of the things I think we talked about, if you are near the equator, you basically have a small, I'm going to go ahead and throw a symbol at you. In physical science, we use the triangle, which is actually a Greek letter for change. So anytime you see me do this, that means change. Okay, here we have a small change in temperature. I'll put T for this temperature. Small delta T. And up here, oh my gosh, look at this. If you lived up here, you would have swings from your summer and this is throughout the year, summer and your winter of 90 degrees Fahrenheit. Oh, I just can't handle that. Yeah, you think we have troubles. Okay, now, let's focus on maybe kind of the continent of North America. Notice that your temperature swings, we see kind of a dip. So basically, your temperature swings inland are greater. So I'm going to put high delta T. High swings in temperatures. Because remember, you don't have the what I keep saying is the moderating effect of a large body of water. So inland, you're going to have great temperature swings. On the coast, you're going to have smaller temperature swings. Okay. Switching gears again. We switched the gears a lot this morning. So we're going to go back to the whole kind of daily temperature cycle. So this isn't throughout the year. This is kind of just your typical daily the temperature cycle. So in the morning it's cold, okay, it gets warmer, and then it gets cold as the sun sets. You guys have all experienced that before. That's all this is talking about. But it's kind of relating it to something that we talked about before, that when the sun has a small angle, we have the beam spreading and beam depletion. Okay, when it has a large angle at noon, we have the least amount of beam spreading, least amount of beam depletion. So throughout the course of the day, it does the same thing as it does throughout the course of the year. So one of the things, or one of the cool, no pun intended, things that happens with our Earth system is during the day, the Earth itself, the geosphere, will soak up energy, and it kind of re-emits that energy in what we call long waves or heat. Okay, it re-emits it right away, and you're going to see a figure here talking about that re-radiation. Re-emits it right away, but it also kind of re-emits it at nighttime, and that's why clouds kind of help trap that outgoing radiation. All right. So I don't know if you've noticed this before, but with regard to sunscreen, okay, your worst time to get a sunburn is probably noon.
Mhm.
Yeah, because it's direct. But your hottest time of the day is what's we call kind of a lag of maximum. So lag means kind of delayed. Maximum in this case is your hottest time of the day. Okay, so basically it's usually hottest maybe 2 or 3 p.m. Now again, you can have kind of an air mass coming through. You can have some other phenomena coming through. It's called lag of max in general. And the reason it does that is because kind of that Earth oozing its radiation back, that's kind of delayed. It kind of soaks it up, there's a little bit of delay, and then it re-radiates it. So it kind of peaks a little bit after the peak of incoming. Okay. So you're going to see a graph here, another graph. And we're going to see that the coolest temperature, the minimum daily temperature, is right before you have to get up in the morning, before the sun rises. Okay? I like camping, but one of the things I don't like about camping is getting up in the morning. I do, but I don't. Okay? And then this kind of cautions that if you have clouds, then kind of this lag of max is kind of a little bit out the door, can be affected. So what this is basically, and we're going to see a device here at the end of your notes that shows you what took this device, but this is just a piece of paper right here, long piece of paper, and they put it on a cylinder and they wind up the cylinder, whatever. The cylinder just kind of moves, and they have a pen in one location, and as the cylinder moves, the pen goes up and down and creates this line. So it's just a way to track the temperature. And notice that it's in military time. That's not the thing to notice. But so, for instance, here we kind of have a peak. Let's see, 1600 hours is 4 p.m., right? So that's about 4 p.m., maybe 3 or 4 p.m. Here we have a peak, maybe about 2 p.m. Okay, we have another peak here. Bless you. This looks about noon. Okay, so that one right there doesn't show the lag of maximum temperature. But this one again is about 2. Okay, this one here, about 2. So that's kind of what it's showing you. When is the maximum temperature? And I like, and we've been talking about this idea of an air mass. And so the slide actually says, it's like, dude, what happened there? And so basically an air mass moved in and kind of affected the base temperature, what I think of. All right. So again, this is looking at down here, this blue curve is kind of like the curve we saw just a minute ago. What is the minimum temperature right before the sun rises? What's the maximum temperature? Oh, this is showing, about 3 p.m. And what this does is actually to show you why that lag happens. So this would be on a clear day, no clouds, okay? And here, this line right here, the red line is the solar radiation. So it is going to peak at noon. You are going to get your most terrible sunburn at noon, okay? But this purple line down here is the Earth oozing it. Okay, so there's a delay in when it receives it and re-oozes it. Re-oozes it. So this is quite appropriate, the whole fog thing, right? So if you've been doing your weather log, one of the things you're reporting is dew point temperature. So dew point temperature is basically, it's always lower than the current temperature, and the dew point temperature is the time at which condensation is going to begin. We're going to see that water vapor, if you take regular old water gas in the air, you cool it down, you can get it to liquefy. So this actually has reached the dew point temperature. My husband got up this morning and he looked at our Roku has the weather thing on it, and he's like, oh, he said percent humidity is 85% humidity. 85% humidity, it must be the fog is gone, and that's right. Fog occurs at 100% relative humidity in general. Okay. So dew point temperatures are basically when you reach that hot spot where basically your relative humidity is 100%. So I mentioned this kind of cooling down. Cooling down is one way to reach 100% relative humidity, and so this is kind of showing two kind of cooling events. Remember we said that your dew point temperatures could actually be frost point temperatures if they're below freezing. So, all right. So latitude, I always have to concentrate. Latitude, what does latitude mean? It's not the same thing as altitude. So latitude means how relatively close to the equator you are or far apart. So as it turns out, in the poles, okay, we said, oh my gosh, you have like a temperature range of like 90 degrees Fahrenheit, right, throughout the year. But your daily temperature change will be less than near the equator. Maritime locations, okay? Maritime locations, what are they? They're on the coast. What does on the coast do? The large bodies of water basically are stubborn to heat and cool. Okay, so their daily swing is going to be less. Makes sense. And as we talked about, this kind of a review thought that if you have clouds, you know, your daily min and max are going to be kind of not what we've been talking about necessarily. Here's another one for you. I think we talked about this, that the greenhouse gases, of course carbon dioxide is a greenhouse gas, but water vapor is also a greenhouse gas. So if you, those high muggy days, actually they can kind of change your range too.
And you won't know if rain is acid rain or not.
You won't know if the rain is acid rain or not?
Because it appears normal.
Yeah, that's true. That is true. Until all of your fishies die.
Then you know.
Yeah. So this actually is a little special topic in your textbook, so I went ahead and snagged it this semester. If you're in the city, a bigger city probably than Keokuk, downtown Keokuk, although downtown Keokuk might have an urban island heat effect going too. Wherever there's a lot of concrete and not very much vegetation, what can happen is basically heat can build up, okay? That concrete is great at absorbing thermal energy, okay, but it doesn't necessarily re-radiate it as much as it absorbs. So it can make the area hotter, and no plants can make the area hotter. So we have this urban island heat effect. All right. So I brought a thermometer today. We talked about all matter is in motion. We said that the thing about matter is if you heat it up, if you zap it with energy, it gets hotter and it goes faster. So one of the things about that is a liquid such as this liquid in the thermometer, as it goes faster, it will expand. Okay, and as it expands, it will go up, and you can read it as a warmer temperature. Okay, that's just the way these work. This is just a liquid and glass thermometer. The color red indicates that it's an alcohol probably, instead of silver might be mercury. So we don't try to get rid of those in the lab. Another way to measure temperature, I'm going to show you a picture of it, but it is basically you have two metals, and the thing about metals is they swell and contract based upon the temperature that the metal is seeing. But different metals swell and contract differently. So actually, if you put two metals together and you know what you're doing, this swelling and contracting can actually bend and needle and give you the temperature readout. I'll show you what that looks like. And then the last one here anyway is this one. So this one actually is what we use. I can beat it up and everything. It's not glass. So this is really handy. Another thing is that, let's see, you're familiar with conducting electricity. So basically, you can take a copper wire, you can put electricity at this end, and you can sense the electricity at this end, because copper conducts electricity. Now, the one thing about that conductivity is that if you were to cool down that copper wire, it will conduct differently. It will slow down. If you cool down the wire, it will conduct slower. If you heat it up, it'll conduct faster, okay? So basically, the how it conducts, okay, or what we call the resistivity, changes with temperature. And so that's how this works, okay? So you just kind of have a closed circuit in there, submit this to different temperatures, and you can measure the resistivity or conductivity and convert that to a temperature. So that's pretty cool. No pun intended. So on the left is a normal thermometer, and then here we have two kind of abnormal thermometers. One of the things you guys are measuring is your your historic high and your historic low for this day in history or whatever. And so actually, if you're not there, you can snag the maximum temperature with this one. So basically, bless you. Basically, you have your little well of fluid here, okay? Your little fluid can go up this way, but notice what it can't do is it can't fall back down. So basically, what you do is you end up snagging the maximum temperature, okay, and it can't fall back down. So the way this works is you have to reset it. So you got the maximum temperature. It's like a little trap. You've got the maximum temperature. You'd have to reset it to go ahead and get that liquid back down there, and you're ready to see another maximum temperature. This one does something kind of similar, but it actually snags the minimum temperature by having kind of a little thing that floats. And it catches the wave down, but it won't catch the wave back up again. So it'll catch your minimum temperature. This is your, I don't know if this looks familiar. This is when we looked at throughout the day, the high temperatures, and this was the little barrel I said kind of spins. I worked at in Middletown at the Army ammunition plant for several years, and so they've got these out there in the plants. So basically, you can, without being there, get a sense for what the temperature is in the plant. One of the things that you don't want to do is forget to tear it off. Like if this is just 7 days, if you don't get it after maybe 3 weeks, basically it's gone around 3 times. You're like, I don't know what that temperature was. Okay. And then this was the 2 types of metal that actually expand and contract accordingly that will make this go up or down. So it's kind of sometimes I look at these things and I'm like, who thought of that? That is so cool.
Who didn't invent this?
I don't know. But what's that?
Who has that much time on their hands?
I know. That's so clever. Probably been around forever. This actually is this sort of technology. Okay, here. It works great for your ASOSs, those automatic surface observing systems. This again is part of an ASOS, and notice they go with white, not black, because white would reflect the temperature, or white would reflect incoming radiation. It's ventilated. Okay, it's a big hairy deal to report the temperature. So I'm kind of tickled. Sometimes meteorologists will they want you to call in rainfall amounts and stuff, but it's a big hairy deal. Okay. So this thermometer actually reads in Celsius. So a lot of times in science, we're all about Celsius because it's metric. But honestly, this doesn't tell me as much as what the Fahrenheit temperature is, you know, if I want to know what to wear, okay? So the Fahrenheit and the Celsius are related at the bottom there. And no, I've never had students necessarily need to do these calculations. But the way this works is if you have the Celsius temperature and you want to know the Fahrenheit, that's what you would use. You would take 1.8 times your Celsius temperature plus 32 to get Fahrenheit. If you have the Fahrenheit temperature and want to know your Celsius, that's what you use. Or you just Google it and you say convert, you know, certain Celsius to Fahrenheit. Yeah.
So we don't need to know that.
You don't need to know that.
Thank you.
Very little math, so. But there's a third temperature scale, and it's also metric, and it's even got more applications in science. And it's related to this idea that all matter has motion. So all matter has motion. So we know that if I were to have a thermometer and measure the temperature of this motion, if I go ahead and cool it down, what happens to the motion? It slows down, yeah. And I can cool it down more and it slows down. But all matter has motion, so when matter doesn't have motion anymore, what does that look like? No one knows. What's that?
It doesn't matter.
It does matter. You know, people have enough time to think about these things. So actually that temperature is called, on the Kelvin scale, absolute zero. Okay? So that's absolute zero. It's negative 273 Kelvin, or 273 Celsius, sorry. So what I was trying to say is, if we have two thermometers right here, okay, this is a Kelvin thermometer and this is a Celsius thermometer. Okay, if we cool down, so molecular motion stops. I'll put motion stops. You have reached 0 Kelvin, and you have reached, on the Celsius scale, negative 273.15 degrees Celsius. So molecular motion stops. So of course that's absolute zero, ABS for absolute zero. Yeah. So this summer, one of the things, and I haven't chased this down, I'm thinking Neil deGrasse Tyson, if you're listening, would be a good person to do this. No, not you, but Neil deGrasse Tyson. So here's the thing. We went to the planetarium, the Adler, in Chicago, twice, actually. And there they say how cold the planets are, which I think is awesome. But they actually, I can't remember how far it goes down, but they use the Celsius scale, which is cool, no pun intended. And my problem is that basically, and again I can't remember, they show like a negative 300 degrees Celsius. Yeah, that's what, I'm just on my list of things to chase down. That just really bothers me, because you can't get colder than, you know, negative 273 degrees. You would think so. Planetary scientists. Yeah. Yeah. I don't know.
It does get colder than that. They just, scientists haven't figured that out.
Yeah, it could be that really you can get colder than
Could be
that.
just an exponential. I mean, it doesn't
Yeah.
ever stop.
Yeah. No. But nice try. He's saying, because I agree. He's like, well, maybe it's really there. But if the scientific community says that the coldest temperature possible is negative 273.15, then I think that unless they publish and just change the thinking there,
Yeah.
they need to stick
What
with this
law
convention.
governs that? It doesn't go past.
It's there's a few. Yeah. I don't
Her
know.
attitude, she's like, nice try.
Nice try.
Yeah, no.
I'll have to think about that. But I think that they should stick with the program. And if the scientific, and especially for us people going through their museum, they should, you know, if there's some obscure sect of scientists that believe you can go to negative 300 Celsius, then they should, I don't know, publish. So here's the three temperature scales. Notice it doesn't go to absolute zero. You know that because if you find the Kelvin scale, that's the rightmost one. You know, the coldest it goes is 253, so we're definitely kind of eking our way down. Okay, but back to normal temperatures. This actually shows you some temperatures we talked about. You know, water, let's see, the hottest temperatures. The hottest worldwide temperature right here. The comfortable, it doesn't show the coldest temperatures.
Is there a limit on how high a temperature can go? If there's a limit on how
As
cold?
far as I know, no, there's no limit. The problem with going with the other direction with hot temperatures is matter, and we talked about this in astronomy, matter tends to kind of fly apart when the hotter it gets, you know, with all that motion. So you end up with plasma and subatomic particles if they're really hot. So,
How do you measure like a super duper hot temperature in measuring tool?
what sort of measuring tool to use with the super hot? It could be probably any of these, you know, I don't know.
But you know,
Yeah, that's true. I see what you're saying. That's true. Because it would melt glass and it would melt.
right.
Yeah, I like that question too. I don't know. Sounds like a good report. So, why don't we, sidetrack, why don't we hold these last two topics, heating and cooling degree days and freezer chill. Wind chill and heat index, we'll hold that for Friday so that your assignment will be due on Monday. So we'll finish this up on Friday. Yeah. Very good.